that mean we're not at a constant velocity, so humans should feel the rotation of the Earth?
That is interesting.
It's an interesting one.
Yes.
If you're on the edge of this sphere, like a human being, you would surely be experiencing deceleration and acceleration.
Exactly.
How does astrophysics at your level explain that?
This physics is talked about by physicists, never ever in association with the rotation we are supposed to be on. See 3 lectures in the description from the well-known physicist Michael von Bison. He explains this physics from simple in lecture 1 to in-depth maths in lectures 2 and 3. Astrophysics runs through calculation after calculation, computation after computation, ignoring one movement, one physics, the physics of all the rotations going around the Sun. At the equator, you are revolving around with Earth at 1,000 miles an hour. At the same time, you and the Earth are travelling around the Sun at 67,000 miles an hour. The relationship between the two velocities changes as the day progresses. That change is constant. That constant change is ignored by physics when it comes to the globe and space. The physics of you on this rotation, Earth, with Earth moving around the Sun. This physics is called rigid body rotation with translation. First vector, 67,000 miles per hour around the Sun. Vector 2, 1,000 miles per hour as Earth revolves. Resultant vector, adding the 2 vectors. Repeat for all 4 positions in 24 hours. All positions have different resultant vector values. At the top it's midday, at the bottom it's midnight. A massive difference in velocities. This is a graphical representation of the 2 constant velocity vectors. Each movement is 15 degrees of rotation in 1 hour. See the resultant vector, the red dashed line. It changes in length as you rotate with Earth. The increase in velocity is shown here. Acceleration value from point to point here. The increase in velocity from point to point here. The Newton force value for 100 kilograms here. Note, the direction of the acceleration and force changes constantly in relation to u. It's self-evident that this physics is taking place. We are on a rotation that is moving. Go and search for any report, article, calculations that takes account of this physics in relation to you rotating on a globe that is moving around the Sun. that shows this change in velocity and describes in any way how it is countered by any force. I don't think you will find one. I've looked. It's not just about acceleration. It's the forces in play, newtons, on a mass of 100 kilograms. Using vector addition, we will first work out the acceleration between 4 points. 2 for 1 hour or 15-degree section. We will then calculate the acceleration between the 2 points. Section from 5 till 6 in the morning, and a section from 1700 till 1800 hours. Then add the gravity vectors. First calculation, resultant velocity at this point, 67,000 mph vector and 1,000 mph vector addition. Using the triangle calculator in the description, put the angle 105 degrees in, then 67000 and 1000. We then get our resultant velocity value. Repeat for the next position. We can now calculate the acceleration. Use the acceleration calculator in the description. Then find the force value on 100 kilograms. Use the force calculator in the description to get the Newton value. We get a force value of 3.2 newtons. Now add the gravity vector. On a mass of 100 kilograms, we have 920 newtons. Again, calculate the resultant vector using 1 degree, then 3.2 and 920 for our triangle sides. We have a reduction in force of 3.199 newtons from gravity at 920 newtons due to acceleration. Now repeat the calculations for 1700 hours to 1800 hours. You may think increase gravity, add more force. This will alleviate the difference. We increase gravity to 1920 newtons. Use the triangle calculator as before, you get 1916.8 newtons. No difference, or very little. We have our calculations. Imagine what this force would do to the trillions of tons of water covering over 70% of the globe. We will look at what happens to a mass of 100 kilograms on a scale as it rotates around the equator. With a force of gravity of 920 newtons on a mass of 100 kilograms at this point, on a scale it will show 100,000 grams. At this point on a scale it will show 100,326 grams. gravity at 920 newtons, then add 3.2 newtons for the acceleration in this direction. At this point on a scale, it will show 99,674 grams. 920 newtons gravity, less 3.2 newtons. This is a change of more than 652 grams, measured mass over one rotation. What other forces are in play, other than gravity? Centripetal acceleration, Sun's gravity, Moon's gravity. To have no difference in measured mass at the 2 points, there must be an equal and opposite force or forces. Centripetal acceleration at the equator is about 0.03 meters per second squared. 0.03 meters per second squared with a 100 kilogram mass, that's 3 newtons. 3 newtons. The 3 newton force is already accounted for when measuring the mass at this point. The force is constant at all points of the rotation. The 3 newton force will not affect the outcome. Next, the Sun's gravity. According to the astrophysicist in the interview, the Sun's gravity has a massive effect on Earth. That this could account for us not feeling any acceleration. Calculation for acceleration on Earth due to the Sun's gravity. Gravity from the Sun on a mass of 100 kilograms is 0.0059 meters per second squared. It's about 0.59 newtons, approximately 60.16 grams of force. The mass is actually 60.16 grams heavier at this point than the scale shows, as the gravity of the Sun reduces the measurement of the mass by 60.16 grams. At the 2 points, the mass will gain approximately 60 grams on the scale, as the Sun's gravity is now pulling to the side. As we're looking at gravity from the Sun, we will have a look at another off-topic problem for the globe, just for a minute. Place the 100 kilograms at this point. With a measured mass of 100 kilograms at this point, including the Sun's gravity, at this point, the measured mass would increase, as the gravity of the Sun is pulling the mass to the ground by approximately 0.5 newtons, or 50 grams, due to the Sun's gravity pulling up at position 1 and down at 2. At point 1, the mass is actually 60.16 grams heavier than the scale is showing, reduced by 60.16 grams due to the Sun's gravity. At point 2, the pull of the Sun gains approximately 50 grams on the scale for the 100 kilogram mass, plus the 60 grams that it is not pulling up as at point 1. We have an increased measurement of the mass of 110.16 grams. (110.16 grams gain in 12 hours. Is everything heavier at night? Do we have the technology to measure this? Do we see this? Will we see this at almost any point on the globe? Back to the main point. For our 2 points, we can add 60 grams approximately to the mass. Makes no difference to the outcome. We still have a large difference. The Newton value is larger as the mass is larger. The Moon's gravity. a small gravity force, less than the Sun on Earth, for the 100 kilogram mass. Will have a similar but smaller effect as with the Sun. We have no equal and opposite force. Any force would have to act in a multitude of directions continually, and continually change that amount of force, including for the International Space Station. This is from the University of Colorado Boulder website. It's a gravity and orbit sim. Have a look, the link is in the description. We're looking at the orbit of the ISS. Remember, the Earth and the ISS are both travelling around the Sun at 67,000 miles an hour. At this point, the ISS is travelling at 67,000 miles per hour with Earth, plus 17,000 miles per hour. Gravity off. The ISS is travelling at 84,000 miles per hour around the Sun. 67,000 miles an hour plus 17,000 miles an hour, as it was when it was orbiting Earth at the point gravity went off. At this point, the ISS is travelling with Earth at 67,000 miles per hour, or less 17,000 miles per hour. Gravity off. The ISS is now travelling at 50,000 miles per hour around the Sun, as it was at the point gravity went off. 67,000 minus 17,000 miles per hour. Have a look at the Sun, Earth and Moon sim part of this. Tick the velocity vector arrows on. Look at the Moon vector arrow. I think someone knows about rigid body rotation with translation. Now for a section of the interview with our astrophysicist.
It is written in astrophysics that the rotation of the Earth is due to, we can't feel it because of constant velocity. Now, one astrophysics guy I met, he said there are two constant speeds. Let me show you this.
Yeah.
And some people I know looked at some rotation physics, and they said if you're on the edge of this, you would be experiencing acceleration and deceleration. It's only the middle point that would experience, like the wizard in the middle. The wizard would be constant velocity, but if you're on the edge, you get acceleration and deceleration because of the two constant speeds. How would you answer that?
You mean why this happens? Or
Well, surely with the rotation of the Earth,
yeah,
and because it's going around the Sun at 66,000 miles an hour,
yeah.
we'd be experiencing deceleration and acceleration. So think of this fairground ride. Pick one human being. So pretend that's the Earth.
So you want to include all the velocities involved, also Earth
Just two.
rotation.
The Earth rotation on its axis, 1,000 miles an hour, and 66,000 miles an hour around the Sun. If you're on the edge of this sphere, like a human being, you would surely be experiencing deceleration and acceleration.
Exactly.
How does astrophysics at your level explain that?
Well, it's gravitational forces. So one gravitational force you have towards the Earth center. So this is gravity of Earth,
Yeah.
and that would holds Earth together, and when it rotates, you experience this acceleration on the edge of the Earth and the gravity towards the Earth. But when the Earth goes around the Sun, there is gravitational force towards the center of the Sun. So two gravitational forces produce this effect of acceleration and deceleration combination.
Wouldn't that mean we're not at a constant velocity, so humans should feel the rotation of the Earth?
That is interesting.
It's an interesting one.
Yes.
The astrophysicist I met, he did a model showing that it should show acceleration and deceleration. So I could actually show you a video where this goes around the sun, and it shows, and even you can go onto the International Space Station, which is orbiting the Earth, and this also should be showing acceleration and deceleration due to the two constant motions, just like the fairground ride.
Right. Well,
probably need some homework.
Yeah, I need some thinking.
But it's an interesting one, yeah?
It is an interesting question, yes. We usually think, that the pull, we have to compare this acceleration to the gravitational pull.
Okay.
That I would start with. Because velocity is one thing, but acceleration is the other thing. So we have to compare acceleration due to rotation to the acceleration due to gravity.
Yeah.
And it's very possible that gravitational acceleration is larger. That's why we just don't feel this side.
I think we would need three different answers. One for the Earth, one for the International Space Station, and then one, imagine an astronaut outside the International Space Station. Yes. How would he be staying with the space station? Because they're all doing this they're all acting under these two constant forces, two constant motions.
Exactly, yeah.
So this is a question I can't get answered. It's a very interesting one.
Yeah, but in this case, space station and the astronaut in space, they are like we call it probe particles, free particles to probe the gravitational field. Yeah. So they will orbit the Earth because of the gravitational pull of Earth, but together with Earth, they will move around the Sun. So, and that is because the gravitational acceleration of the Earth to the Sun is much larger than gravitational acceleration of any of us to the Earth.
So they just don't notice it?
Yeah, they don't notice this.
Okay.
So that is, I think this, of course, the rotation around the Sun, orbiting around the Sun, it's a huge velocity. But we're so pulled to the Earth that this Earth to the Sun is somewhere. you.